This video is over topic 48, test accuracy tables. So some things to know as a background. You want to know where the true positive, true negative, false negative go in the table. So that's this. The true ones, upper left and lower right. False ones in the lower left, upper right. Want to know that. And then in general, you want to just start with the given information. The accuracy rates are always as a percentage of the row total. You want to know how totals work in a table again. Everything in the row adds up to the total. So if you know the things in the row, you can find the total. If you know the total on one of the things in the row, you can find the other thing in the row. So you're going to work your way. Basically, you're going to have these 9 places you're going to fill in. You're going to start here, and then you're going to go usually to here. And then from there, you can go get the rest of that column, and you can get the first row. And then once you have the column or the row total, and then once you have both the the column values, then you can get the column. So essentially, that's kind of, let's see if I can. So starting with this, that's going to get you to this. That's going to get this. And one of these, whichever one of those you get, gives you the other one. And then this is going to give you one of these. And whichever one you get the other. And then those combine. And those combine. Still maybe not helpful. I don't know. But you're kind of going in this like counterclockwise circle. You're not going, the important thing here, you're not doing like a left to right row to column, right? That will not work. You got to start with the total and work your way back. All right, let's look at about 3 or 4 examples of this process. So I usually start with the given information, put it in the appropriate places in the table. Suppose a population is 30% diabetic. That's the have diabetes total is 30%, and it is 30% of the total. Okay. So I represent that with just a down arrow under the 30 to remind me that that is a percent of that, the total of that column. The test for diabetes is 94% accurate. I'm going to write as a reminder here, this is the true positive test for somebody that has diabetes. Negative test for someone that does not have diabetes is the true negative. So those are going to be the accurate results. Whereas the negative test for somebody that has it is a false negative. Positive test for somebody that doesn't have it is a false positive. So the accuracy rate, the 94%, is going to be the true positive and the true negative. Now, each of those is going to be a percent of its row total. So 94% of the total that have diabetes, 94% of the total that do not have diabetes. And then we're going to use a population of 10,000 people. That's going to be the overall total. All right. So with that given information, so that's kind of what this is walking through, getting from just getting the given information in the appropriate places. Then the order you want to do, first thing is figure out the total column. So starting with 30% here, 30% of 10,000 is 3,000. And then this one is 10,000 minus 3,000, which is 7,000. Now, I don't have to do the 7,000 second. I could go, as soon as I have the 3,000, I could go and finish, do the whole have diabetes row. So, it's not necessarily a one right order to do it. But now I'm going to go to the have diabetes row, and the positive test, the accurate tests, are 94% of the row total. So this is within the row. It can only be within the row. So the 94% is not 94% at the 10,000. It's only 94%. It has to be a portion of within the row total, within those 3,000. So there's 3,000 people that have diabetes. 94% of them get a correct positive test. 94% of 3,000 is 2820. And then I use that to find, so the rest of the 3,000 are the ones that have diabetes and get a negative test. So that's 180. All right, then for the do not have diabetes, the accurate tests are over here in the negative test column, and that's going to be 94% of 7,000. Which is 6,580. And that means the ones that don't have diabetes get a positive test are the rest of the 7,000. So 7,000 minus 6,580 is 420. Right, and so then the last thing to do here is to add up the columns. So this is 3,240. And then 180 plus 6,580 is 6,760. And then as a final check, does 3,240 plus 6,760 equal 10,000? Yes. If it doesn't, it means I've definitely made a mistake. If it does, it's still not guaranteed that something didn't go wrong, but at least nothing obvious. Now, once you have the table filled out, you'll use it to answer questions. So the 30% have diabetes is just with no test, just the what's called the prevalence in the population. 30% have diabetes. Any given random person, all they know is 30% chance that they have diabetes, 70% that they don't. So if a person gets a positive test result, it doesn't 100% guarantee that they have diabetes, but it does make it more likely than if they hadn't taken the test. So we'll have these conditional probabilities if a person gets a positive test result. So we're looking at just that first row, the 2820, 420, and the 3240. So this is the positive test results. 2820 of those have diabetes, 420 do not have. So this is out of 3240 has diabetes is the 2820. So as this person, they don't know if they have it or not. All they know is what the test tells them. But based on the test accuracy and the prevalence, then we can say, all right, you have that test. Not 100% guarantee that you have diabetes, but it is 2820 out of 3240 is 0.87. We would say 87% probability. A lot higher than the 30%, but still not guaranteed. Probability the person does not have diabetes is the other 420 out of 3240, and that's going to come out 0.13. So instead of a 70% chance they don't have it if they hadn't taken the test, now they have a positive test in hand, they're down to a 13% chance they don't have it. Still possible, but a lot less likely. Now, if a person gets a negative test result, now we are looking at the negative test column. So that's the 180, 65, 80, and the 67, 60 total. So those people with the negative test, 6,760 of them, 180 actually do have diabetes and got a wrong test. The other 6,580 don't have it, and the test is accurate. So with a negative test, probably the person has diabetes is 180 of the 6,760. So doing that division, it's 0.03. So no test at all, 30% chance they have it. If they're holding a negative test in hand, down to still a small chance, still a 3% chance that they do actually have it, but much lower. And then probably the person does not have, that would be the 6580 out of the 6760 is now 0.97. They're up from 70% chance they don't have it to all the way to 97%, but there's still a small chance that they actually do have it. All right. The test accuracy affects the false positive, false negative rates. So does the prevalence. So let's look at what happens if we go instead of a 30% prevalence to a lower prevalence, the actual 12.4% in the US for diabetes. So we're still going to use 10,000 people to start with. So our initial given information, we have 10,000 here for the total. 12.4% prevalence, which is the percent of the population of the total that have diabetes, and then 94% test accuracy. So 94% of those that have it get a positive test, 94% of those that don't have it get a negative test. So starting with finding the total that have diabetes is 12.4% of 10,000. So that's 1,240. And just to show I can go a little bit different order. Once I have this, I can go ahead and do the rest of this row. So now the positive test for those that have diabetes, 94% of 1,240. Now, do not round, keep all digits. So we'll leave this as 1165.6. And then we can find the rest of that row. So the rest of the 1,240 will get negative tests. $74.4. All right, then I could go on to the ones that do not have. So the rest of the 10,000, other than the 1,240 that do have, is 8760. And then I go, all right, of those 8760, 94% get a correct negative test. $82.34.4. And then I can calculate the rest of the 8760 at an incorrect positive test. That's 525.6. And then finish things out by adding the positive test. There's a total of 1691.2. And then the negative tests, there's a positive total of 8308.8. And I just do a final check. Do those add up to 10,01691.2 plus 8308.8? Do in fact add up to 10,000. So as far as I know, that's at least not an obvious error. All right, so let's break this down then to what this means. So no test, random person out of the 10,000 people, 12% have, 0.124 probably that have, 0.876 do not have. If they get a positive test result, now we're looking out of the 1691.2 positive test results. 1165.6 have it. The other 525.6 do not have it. So those probabilities 0.689 and 0.311. And then for those that get negative test results, out of those 8308.8 people standing there with negative test results, 74.4 actually have it. The other 8234.4 don't. Zero point zero zero nine. All right, so now the person, they don't know if they have it or not. If they didn't take the test, 12.4 chance they have it, 87.6% chance they don't. If they've taken a test and they sit there with a positive test, still only 68.9% chance they have it, 31.1 chance they don't. So still pretty good chance as the prevalence is lower, that means it's that much more likely that you have a wrong test versus that you actually have the disease. So lower prevalence results in more false positives versus the negative test result. All those people sitting there with a negative test result, there's a less than 1% chance that they actually do have it versus over 99% chance they don't have it. Lower prevalence causes lower false negative, fewer false negatives, but more false positives. All right, let's look at another example. So 10% of the US population is allergic to cats. Put that here, 10% of population, the overall total. A test for allergies states that those who are allergic will test positive 80% of the time. So I'm going to put the 80% in the are allergic positive test. And that's a percent of the total who are allergic. And then people without a cat allergy will test positive 10% of the time. So that's the not allergic positive test. And again, that is of that row total. So the accuracy rates can be different for those who have and those who don't have the thing being tested for. And we're going to test a group of 10,000 people, so that goes here. So starting with the total row, 10% of 10,000 is 1,000. And that means the rest of the 10,000, 1,000 people that are allergic, 9,000 that are not. Then of those who are allergic, 80% of those 1,000 get a correct positive test. And that leaves the rest of the 1,000, 200 people, getting an incorrect negative test. For those that are not allergic, 10% of those 9,000 get an incorrect negative test, or sorry, an incorrect positive test. 10% of 9,000 is 900. And the rest of the 9,000, 8,100 people, get a correct negative test. And so there are a total of 1,700 positive tests handed out and 8,300 negative tests. 1,700 and 8,300 add up to 10,000 as a final check. So we're looking at the probabilities. If someone receives a positive test result, what's the probability as a false positive? So there are 1,700 positive results. The false positives are the ones that are not allergic. So that's 900 are false. So 900 over 1,700. What is that? 0.53. Then if someone receives a negative test result, so there are 8,300 negative results. What's the probability it's a false negative? The false negatives are here, the negative test on those who are allergic. There are 200 of those negative tests are false, so 200 out of 8,300. Zero 0.02. All right, then we can still have other types of probability questions from this type of table. So if someone has an allergy to cats, so we're looking at the 1,000 that are allergic. What is the probability that person will receive a positive test result? So that was 800 of the 1,000 allergic people received a positive test result. 800 over 1,000 is 0.8. If you look carefully at this question, this is asking the exact same thing as what it said up here. That those who are allergic will test positive 80% of the time. That means the probability that someone who's allergic will test positive is 0.8. So that's really asking that, but you don't need to recognize that if you just follow the correct conditional positive probability process. Then part E, what is the probability of randomly selected person? So now we're just going out of the 10,000 will receive a positive test result. So we're looking at out of those 10,000 people, there was a total of 1,700 positive results. 1,700 out of 10,000 is 0.17. Okay, then one more example. This is drug testing. So we have 4% of employees use drugs. we're looking at a company with 8,000 employees. And there's a test that reports a 5% false positive rate. So again, using drugs positive test, true positive. Using drugs negative test, false negative. Not using drugs positive is false positive. Not using drugs negative is true negative. So false positive rate is going to go here, 5% of that row total, and 10% false negative is going to go here, 10% of that total. So starting with the total, doing 4% of 8,000 is 320. Then we can go, all right, the rest of the 8,000 minus 320 for the total not using is 7,680. Then the using drugs, 10% of the 320 is 32 people that are using drugs but get a negative test. So those 32 might be a concern to the employer or not, depending how seriously they need to take it. If this is something where using drugs could endanger other people, then they might need to figure out like there's some way we got to find these 32 people, looking at other symptoms, repeated testing, doing tests regularly makes it that much more likely somebody's going to keep slipping through the cracks. But that's still, out of 8,000 people, a pretty small group. Then that leaves the rest of the 320 of those using drugs, the 288 that do get a positive test, and the company can say, all right, you guys, now they don't know though, so there's 208 people that are using drugs get a positive test. The employees know that they're using. The company only knows they got a positive test. Because let's look at the not using drugs. 5% of the 7,680 people that aren't using drugs also get a positive test. 384 of them. So now we have a total, all the company knows is that they have 672 positive test results. More than half of those people are saying, I promise I don't use drugs. Probably a lot of them, probably all of them are saying, no, I really don't use drugs. But over half of them are truthfully saying, no, I don't actually use drugs. Company has no way of telling. But again, if they know this information, they can figure out that, like, all right, these positive tests don't actually for sure mean that these people are using drugs. Now, the other thing that happens is that the other, so this was, we went here, came here, and then here, and then the rest of the 7,680 7,296. So there's these 7,000 people looking probably at the 384 people saying, the 7,000 people are saying, I'm not using drugs. I got a negative test result. Like, what are you talking about? I don't believe you that you say you're not using drugs and you got a positive result. It didn't happen to me. Why would it happen to you? But statistically, it is going to happen to some people. And then we have our, I guess I did this, and then our total 32 plus 7296, 73, 28 total negative tests. So the company only knows they have the positive tests, they have the negative tests. The negative tests pretty good chance there's only a few of those that are wrong. So pretty good chance those people are okay, but maybe those 7,300 people, 7,296 people, like still need to be prepared that like to chase down those 32 that are getting away with it. Like they're going to have to keep getting tested to make sure, because it could be one of those 32 and getting, even though they have a positive test, could totally be doing drugs. But yeah, so just the positive test is not a guarantee that they are doing it. Negative test isn't a guarantee that they're not doing it. But the negative test is closer to a guarantee. It's a lot more, a lot fewer false negatives than false positives. All right, probability an employee is using drugs given they tested positive. So out of those 672 positive tests, 288 were actually using drugs. 8 divided by 672 is 0.43. Still, given they tested positive, out of those positive tests, 384 were not using drugs, and so that's going to be 0.57. So again, if you treat all positive test results as true, then you're hurting those 384 people, because you don't know which is which. So you want to give some benefit of the doubt. It depends on the company, again, what they're doing. Are they going to, say, sorry, you may or may not actually be using drugs, but it's a serious enough issue if you are that we have to assume you got a positive test. We're going to act accordingly, whether that's maybe some sort of suspension or further testing, or maybe it's even an immediate dismissal. But understanding as that's whatever is happening, that like it could be that you just got a false negative that didn't mean, or a false positive rather, and you're actually fine, rather than assuming that all of those 672 results were people actually using drugs. So further testing, monitoring for other symptoms. So are they groggy? Are they seeming out of it? Whatever things that are potentially signs of drug use, or maybe the opposite, maybe super productive and alert or whatever, depending on what's being tested for. Then if an employee receives a negative test result, so that's out of the 7,328, there were only 32 of those not using. So 32 divided by 7,328 is 0. We'll go to let's play 0.004. Or sorry, not using 7296. It's going to be 0.996. So it's still so 99.6% probability that they're not using drugs when they get that negative test, but it's not 100% guaranteed. Unless you have a test that's 100% accurate, which doesn't exist. Like there's going to be errors. It's not going to be 100% guaranteed. So you want to, again, not assume that the test guarantees or means anything, and you have to kind of weigh the potential issues of a false positive and treating that as true versus treating a false negative as true versus treating a true result as a false result. Like all of those have potential problems they could cause, and so you have to, there's more to it than just doing the calculations, and there's certainly more to it than just doing the test and saying positive, therefore this is true, or negative, therefore that you're fine. So that's the test accuracy tables.